Start. So welcome to the third day of the virtual school on electron-phonon physics and the EPW code. I'm Mario Zacharias, one of the instructors of the school, and I will be the chair of today's session. So our first lecture for today is on carrier transport and the Boltzmann transport equation by Samuel Poncé. And this will be followed by another lecture on phone-assisted optical processes by Emmanuel Kipakis. So this should take around like 1 hour and 1 hour. So enjoy the lectures. Thank you.
Thank you very much, Marius. Thank you for joining for this third day. And so in this lecture, I will focus on the transport part of EPW, and I will also build on the lecture of Feliciano from yesterday. So the plan for the lecture is first I will start by describing sort of carrier transport from an experimental perspective. What are the results and what we are looking for? And then I will try to make the connection between a fully quantum theory that was introduced yesterday, and with a set of approximation, I will show how to get the Boltzmann transport equation, which we will then use to obtain transport properties such as conductivity, mobility, resistivity, and things like that. I will give some technical detail linked with the implementation in EPW, and then I will show some application to semiconductor and metals and sort of slightly introduce what we will do during the hands-on. And I will finish by describing ionized impurity scattering, although this is not fully ab initio, this is using a model, but it's just to sort of give an idea of what can be done and what we can expect. So in a very general sense, if you apply an external electric field to a material, so this could be, if you have a transistor, you apply a voltage to the materials, and then the carrier, so the electron or the hole, will start moving as a result of that applied field. However, this movement will be impeded by various scattering mechanisms. So it will be slowed through interaction with the lattice. So this is electron-phonon interaction, but there are also other scattering mechanisms, such as scattering with other charge. This is ionized impurity scattering. You can have defect scattering, you can have grain boundaries, and things like that. So in this talk, I will mostly focus on electron-phonon scattering, and so the fact that the charge will be slowed down through its interaction with the lattice in which the charge is propagating. And in sort of quite pure semiconductor, this is indeed the dominant scattering mechanisms. And so we could say that the mobility is proportional to the occupation of the state times its carrier velocity and how that change with the applied field. And so from a sort of what happened experimentally or in an experiment is the fact that you can have either you can dope a semiconductor or you can have intrinsic doping. So intrinsic doping means that due to temperature, you can have charge that goes from the valence band into the conduction band. And you can have an indirect semiconductor or you can have a direct semiconductor. So this is silicon, this is gallium arsenide. And what I want to emphasize is that the charge that are really the one responsible for the transport properties are really living at the edge of the bands. So in the case of the conduction of electrons, so the electron mobility, it's really the charge at the edge of the conduction band. And in the case of the hole, it's the charge that are at the edge. And so it's really crucial that we describe the electronic properties of those states very well, because the transport property will be affected by mostly an energy scale which is very close to the band edge. So this is just to show you, so this is both DFT and experiments, the change of intrinsic carrier concentration, the increase as you increase temperature. So note that this is an inverse scale. So as I go here, my temperature is increasing. And so the carrier will be populating the conduction band. And so this is also to show sort of a magnitude, an order of magnitude. So in a bulk semiconductor, you can have carrier concentration that goes from 10 to the 12 to 10 to the 18 intrinsic doping, so centimeter minus cube. And of course, and this was mentioned yesterday, as you increase the temperature, there are many things that will change. So first of all, the bands will be affected by temperature through the electron-phonon coupling, but also through thermal expansion. And so the band gap will decrease. And so in most cases, the band gap closes, but it was shown yesterday that in some cases, the band gap can also open. And so in this case for silicon, you can see that the conduction band goes down as the temperature increases and the valence band goes up. And what I'm showing now here in blue and red are the position of the Fermi level to obtain the given carrier density, carrier concentration that you see in those numbers. And this is if you want to have p doping, so if you want to put holes, and if you want to have n doping, then this is the red lines. And so, for example, if I want 10 to the 12 carrier concentration, I need to put my Fermi level here, and this will then populate carrier through the Fermi-Dirac distribution function like that. If I want to have a more carrier than, for example, 10 to the 14, then you can see that the Fermi level is going down closer to the valence band, and the same, but for the conduction band in the case of electron. What you can also notice is that those numbers are different, and this is simply because in silicon, the conduction band has 6 pockets along the gamma x direction. And so when you're populating those 6 pockets, it's not the same as populating just the valence band. And so this is why you have this asymmetry. Now, if you then put many more carriers, so if you increase the carrier concentration, then at some point, the mobility will start decreasing significantly. And this is because of this impurity scattering that is coming into play. So basically, the electron traveling interact with the other electrons when the density is dense enough. And so in all the calculation we will do in the hands-on, we will be in the regime, maybe below 10 to the 16. So in the regime where the mobility does not change with carrier concentration. And so this is this intrinsic sort of doping regime. Now, if you look at a fixed carrier concentration, and then you look at how the mobility change, and those are experimental data, as you increase the temperature, you can see that the mobility is dropping because as the temperature increases, the phonons vibrate more, the atoms vibrate more, and therefore the electron will interact more with the phonons, and therefore this will reduce the mobility by increasing the scattering. And so those are the intrinsic sort of very pure silicon sample, and the lines that you see here with 10 to the 17 are the ones that are much heavier doped. And you can see that the mobility is reduced and also further reduced by temperature. Okay, so the goal of the theory will be to try to compute and predict such mobility or such conductivity fully from ab initio. And so we can come back to the talk of Feliciano yesterday showing the many-body derivation. And so in that framework, the current density will be expressed as the gradient of the lesser Green's function. Notice that it's at equal time. And so we can define our Green's function in terms of field operator, as was shown yesterday by Feliciano. Now, the difference is that here you have those brackets, and this is simply a thermodynamical average where you have also a partition function. And this is because I'm interested in a temperature-dependent Green's function, whereas yesterday Feliciano showed the zero temperature Green's function. And so you can express those in terms of Schrödinger field operator. And what we would like to do is to compute those Green's function. And so the standard way to do that is to use perturbation theory. And so what we would like to do is to do a perturbation expansion. Now, the issue is that you can see that we have Hamiltonians here. We have also some Hamiltonian in the denominator. And the problem is that they don't commute. And so it's difficult to do a perturbation expansion. And so one solution is to use a contour where basically you have some time in the past, and then you go in the future, and you go back, and then this leg, the complex leg, is to describe the temperature. And so if you rewrite the Green's function on the contour, then you have this time contour operation, the time ordering operator on the contour. And in that case, then the operator are well defined on the contour. And you can also expand your Hamiltonian in complex time, and you can expand it as a non-interacting Hamiltonian, an interacting one, and then one that contains the external field. So in this case, it would be an external electric field, but you can also have an external magnetic field, and so on. And so then what we can do is we can do this perturbative expansion. So we expand our Green's function in power of the interacting Hamiltonian and the external Hamiltonian. And so we obtain the non-interacting Green's function, which I've written here in terms of the two field operator. And then we have this expansion. So it's basically a Taylor expansion of our Green's function. Now, when we have this, we can express the Hamiltonian in terms of their field operator. We can use Wick's theorem in order to rearrange by pair all the field operator and to write all the Green's function in terms of the non-interacting one. And then those corresponds to a Feynman diagram. We can solve the expansion and we can obtain the Dyson equation, which was also shown by Feliciano yesterday here, where we have introduced this self-energy. So again, the notation, one means position and complex time. And then what we can do is we can use Langret rule. We can define the inverse Green's function. We can explicitly write the non-interacting Hamiltonian. And we can evaluate the Dyson equation at equal time, because I remind you, what we are interested in is the current density. And so what we want is the equal time Green's function. And so if we do that in the limit of t0 going to minus infinity, then what we can do is we can break this Green's function into many different terms, depending on where they are on the contour. And so we will have a lesser Green's function, a greater one, a retarded one, etc. We'll have 7 Green's function. And for each of them, we will have an equation of motion. And so here I've written one of the Kadanoff-Baym equation of motion. And so this is the most general equation of motion without any approximation. And so we have that the change, the time evolution of the lesser Green's function is given by those 3 terms. So the first one is the unperturbed time evolution of the Green's function in a static potential. The second one is the local time self-energy. And I'm saying local because you can see that the self-energy has only one time index. And the last 4 terms contains all the internal dynamics. So it's all the collision, all the scattering that are contained in those self-energy and G multiplication. And so now what we are going to try to do is to make some well-defined approximation to obtain the Boltzmann transport equation. And so the first thing we can do is we can consider electrons in a solid, because we want to describe how carrier propagate in a solid. So we can describe it as a kinetic term plus a lattice and exchange correlation potential. And if we do that, and we also do this approximation, then one can show that the first term is actually 0. So we drop the first term. Now, the second term, if we consider that the external field is spatially homogeneous, and this is not really an approximation in the sense that most experiments, you will apply an external field. And typically, from a microscopic point of view, the field will be homogeneous, in space, even though the field might be AC, so it might be time dependent. And so you obtain this field, and if you then block project the Green's function, and here I've introduced this definition of the lesser and greater occupation function, and this is just by definition the block projection of the Green's function on those periodic wave function, if you want. And if you do that, one can show that you obtain this much simpler sort of form. So you obtain the external field, time dependent, times the change of the block projection of the Green's function and the change with respect to momentum. And so then we obtain the Boltzmann transport equation. So with those 3 approximations, we can obtain the time-dependent Boltzmann transport equation, which we call the AC because it's time-dependent. And so instead of the G, now I have this block projected G. So I have this F, so this lesser occupation function, and the change of that with respect to time. And then this is the term that I have shown, and this is the driving term. So this is the term responsible for the movement of the electrons. So this is linked with the application of the external field. And that should be equal to the collision rate. And at this point, I have made no approximation to the collision rate. I've just defined this gamma. And again, the gamma is the block projection of the self-energy. And so the Boltzmann equation is an equilibrium equation where we equate in one side all the driving term, everything that pushes the electron to move in the materials. And this is equal to all the collision, so everything that slows down the electrons. Okay, so now we can do a further simplification. So the first thing is we can consider, again, this is not really an approximation, we can consider that we have a time-independent field. So we have an experiment where we applied an external electric field, and that field is time-independent. If this is the case, of course, the first term being time-independent, it just dies, and you're left with the two terms. And in this case, so the term in red before, because it will now only depend on time differences, you can do a Fourier transform, and now you only have a frequency. And if you define this f as the frequency integral of this lesser occupation function, you now have the real occupation function, meaning the occupation of the state. So this is the out of equilibrium occupation of my state. However, this is not the Fermi-Dirac distribution function because this is still dependent on the external field. And now we are left with the collision term. And of course, the self-energy is a very complicated object, so we need some further simplification. And so if we do all of those approximations, we consider only electron to one phonon, so we neglect phonon-phonon interaction. We consider static electron-phonon interaction, adiabatic phonons, and this delta approximation. If we do all of those approximations, then we can simplify this collision term, and we can show that this is equal to the electron-phonon matrix element times those 4 energy-conserving terms. And those correspond to those 4 situations where you basically have an electron or a hole leaving the state Fnk by absorbing or emitting a phonon, and you have the reverse. You have an electron coming inside the state Fnk by absorbing or emitting a phonon. So those are the 4 possibilities, and they are described by those 4 lines. Just to recall, so the G that you see here has been introduced yesterday by Feliciano in his lecture. And so this is the electron-phonon matrix element, and it's basically the change of the self-consistent potential with a phonon sandwiched with the periodic part of the wave function. Okay, and so if we do all of those approximations, actually what we obtain is, so this equation here is the Boltzmann transport equation. So it's the equality between this driving term, proportional to the electric field, and those collisions. Okay, so now that we have that Boltzmann transport equation, we can come back to what we originally want. So what we originally want to compute is the conductivity. And the conductivity is linked with the current density. But what we want is we want the macroscopic average of the current density. So we just do a space integral of the first slide where you had the current density. And so if we do this spatial integration, then again, by doing all of those approximations, we can show that the lesser Green's function, we can block project, we obtain this lesser occupation function, and then we can integrate in frequency, and then we obtain this occupation function. Now I've indicated that this depends on the field to tell you that this is the out of equilibrium occupation function. And so now my macroscopic average of the current density is simply the carrier velocity times this out of equilibrium occupation function. Now, by definition, the conductivity is the linear response of the macroscopic current density with respect to the external field evaluated at 0 field by definition. And so this is nothing but the velocity times the change of this occupation function with the external field that I'm applying. And so here I'm just using this shorthand notation, but it just means the derivative with respect to the field evaluated at 0 field. Now, in practice, experimentalists, they like to define what is called the mobility, because in a semiconductor, the conductivity will depend on the doping. So on the number of carriers you have. The more carrier, the bigger, the larger the conductivity will be. And so in order to have a more intrinsic properties of the material that does not depend on doping, they've defined this mobility as the ratio between the conductivity divided by the carrier density. And so this is the definition of the drift mobility. Okay, so this is the drift mobility. And what we want to compute the drift mobility is this change of occupation with respect to field. And so how to obtain this? We can go back to our Boltzmann transport equation, which is here. And we need to do the derivative of that equation with respect to E, with respect to the field. So if we do on this side, of course, this drops. And then we do on the other sides, and all the F will become the F. But then you can also show that some of them will become F0. And the F0 is the equilibrium occupation function. So this is really the Fermi-Dirac distribution function, while this N are the Bose-Einstein distribution function, again, equilibrium 1. And then you have those energy conserving delta. And so this is what we call the iterative Boltzmann transport equation, because in order to compute this term that you need here, you need to solve this equation self-consistently, because it also appears on the right-hand side at a different band and different k points. And I've also introduced this tau, which is the scattering rate. And the scattering rate, as you can see, is proportional to the electron-Phonon matrix element itself, and also is proportional, closely linked with the electron-Phonon self-energy. Now, in experiment, most experiments are not drift mobility. So drift mobility would be measured through a time of flight experiment, for example. However, this is difficult to do experimentally, and so most measured mobility are actually measured through what is called the Hall mobility, so through a Hall experiment. So the experiment is like this. You basically have, you apply a current, so you have the electron flowing in the materials, and then you apply a magnetic field orthogonal to the sample. And because of the Lorentz force, the electron will be deflected on one side of the materials, and this will produce a potential that can be measured. And so we need, if we want to describe Hall mobility, we need to augment our Boltzmann transport equation, because we need to add this additional driving term, because this, so the additional force that the electron will feel, the Lorentz force, need to be added into the Boltzmann transport equation. And so it's basically the same equation as before, but we have this additional term. And ab initio, this was something first done by Francesco Masceda in 2018. And he will help us for the hands-on, and he helped us, of course, implementing also this in EPW. And so if we want to compare with experiment, we really need to add this term. And so experimentally, what they also usually report is what is called the Hall factor. So the Hall factor, this R, is what is an adimensional factor that connects the drift mobility with the Hall mobility. And so this adimensional factor is defined as this drift mobility and then basically this Hall mobility. So divided by those drift mobility square. And also this is done at finite but small field. So we are going into the limit of a vanishing field. And so this also tells you that a magnetic field has the unit of, of inverse mobility. Okay, so now, if you don't want to solve this equation self-consistently, what you can do is you can simply kill the second term here. And this is what is called the self-energy relaxation time approximation. So if you do that, you have this Boltzmann equation where the second term was just removed. And in that case, you can show that basically this object, this object now depends directly on the scattering rate. And because the scattering rate is the inverse of the imaginary part of the electron-Phonon self-energy, we are calling this the self-energy relaxation time approximation, because it links it links basically the mobility directly with the self-energy. Okay, so now also I'm showing throughout the presentation on the top right side, I'm showing input variables that are connected with EPW. And so now, if we want to do those calculations in practice, you can notice that we have a double momentum integral. We have a k-point integral here, but then we also have a q-point integral. You can see the q-point here, but also in the tau. And so we have to perform those two momentum integral. And as it turns out, this converge very slowly with the number of k-point and q-points. Therefore, you need extremely dense grid, and you need to evaluate this electron-Phonon matrix element on extremely dense grid. And so this is the purpose, or this is one of the solutions, is to use the EPW code, whereby, and this was introduced yesterday, whereby you compute the electron-Phonon matrix element or the dynamical matrix on a coarse grid. You use maximally localized Wannier function to transform those quantities into real space, and then you do a Fourier interpolation onto very dense grid, and this allows you to converge those integral very accurately. So now we can look at the electron-Phonon matrix elements, or more precisely, we can look at the deformation potential, which is the matrix element, but then you can see that we have multiplied by the Phonon frequency. And here I'm showing the deformation potential of cubic boron nitride. And I'm showing this at the k equal gamma point along the Q high symmetry lines. And I'm showing that for all the bands, all the phonon modes of cubic boron nitride. So you have 6 branch. You can see them here. And so this is the LO, TO, and then the acoustic mode. As you can see, you have the LO mode, which is diverging as 1 over Q as you approach Q equal gamma, so in the long wavelength limit. And of course, when you do this Fourier interpolation, and this was also introduced by Fröhlich yesterday, the problem is that in order to do an accurate Fourier interpolation, you need something that is very localized in space. And so by definition, those long range effects will not be localized in space. They will be very long range. And therefore, the strategy is to remove the long range and then to do the Fourier interpolation and then to add it back at the end analytically. So you can notice 2 things. We have this divergence. And then for this branch, for example, we have this discontinuity at the gamma point. And so in 2015, this was realized. And so in the context of electron-Phonon, but of course, this was realized much earlier in the context of the dynamical matrix and the phonon band structure. And so the strategy is to split the electron-Phonon matrix element into a short range and a long range part. Now, the long range can be Taylor expanded in a multiple expansion, the first of which is dipole, then you have quadrupole, octopole, etc. And so the dipole have this analytic form where you can see that you have Q, G plus Q, you have the Born effective charge, and then you divide by Q the electric function, and then Q. And so you can see that you have a 1 over Q divergence, and this is shown by this basically LO mode going to sort of infinity at gamma. And so now the issue is this discontinuity. So now if I will zoom in on this deformation potential, and I'm now showing what you get. So you do recover the divergence, I mean the 1 over Q, but now what you can see is that we don't interpolate correctly these non-analyticities when you're going towards gamma. And so here what I'm showing is basically when we remove or when we approximate this long range with only the dipole term. And so we've added we've subtracted and added back the dipole at the dynamical matrix level and at the electron-Phonon matrix element level. And so something that was discussed very recently in 2020 is the fact that in order to describe those discontinuities, we need to also add more terms in this long-range expansion. And so this is the quadrupole term, which has this form that is given here. And notice that in this case, we have QQ divided by QQ. So we have something that does not diverge, but it will be direction dependent. So it will come and have it will come with a different value as you approach gamma. So now, as you can see, I have applied this strategy of removing and adding quadrupole on the electron-Phonon matrix element, but not on the dynamical matrix. And you can see that the interpolation is therefore not perfect. And the reason for this is that, as you can see, we have here this eigen displacement vector. And so it's really important to also add this quadrupole at the dynamical matrix level, because then you will obtain, when you diagonalize it, you will obtain eigen displacement vector. And so if you don't include them as is done here in orange, then those eigen displacement vectors are not correct and you get those spurious interpolation. However, if you include it also at the level of the dynamical matrix, which was done in this paper, then you can see that you have a dipole-dipole term, you have a dipole-quadrupole term, and then you have a quadrupole-quadrupole term. And if you do that when you do the subtraction and addition back, then you finally obtain a good interpolation, which is this green line you can see that we correctly go to a finite value here, and then we go to a different value as we approach gamma from a different direction. Okay, and this can be done in EPW using this quadrupole file that we have to provide to EPW. So now I want to touch briefly on convergence. So what I'm showing here is the electron and the hole mobility for 10 simple semiconductor. And I'm showing this as the coarse K point and Q point grid convergence for a given fine grid, And as you can see, the mobility converge relatively slowly with the grids. So you have to go to quite dense coarse grid. And so this is the mauve curve. And the reason for that is because of the electronic Wannier function. And so what I'm showing here is a zoom in the case of silicon on the conduction band minimum. And this is how the interpolated Wannier bands look like if I'm using an SP3 projection or if I'm using an S+D projection. And of course, I need to mention that this is a bit of a pathological case because the conduction band minimum is not at a high symmetry point. Therefore, it's not part of the original grid on which you ask Wannier to do the interpolation. And therefore, it's difficult for the Wannier function to find, for example, the minimum. So you can see that this minimum oscillates, and you need to go to quite dense grid in order to converge the result and re-obtain the DFPT result. And so this is the main reason why the mobility converges relatively slowly with the K-point grid density. The other reason is also linked with the velocity, and for that one can also improve the velocity, but I will not discuss this. But basically, you can get sort of a speed up. And so in what I'm showing now in orange is the convergence if you're using the electronic degrees of freedom that are converged, and you look at the phonon degrees of freedom. And in that case, in most cases, converge much faster. And so this is a hint that the issue is really the slow convergence of the Wannier function in some case with respect to coarse K-point grid. Once you're happy with the convergence of the coarse K-point grid, then you need to converge the fine grids. And so what I'm showing here is on an inverse grid. So this is 1 over the grid. So for example, here I have 1 over 150. So this means that I'm doing an interpolation on a 150 by 150 by 150 K-point and Q-point grid, both the K-point and Q-point. And so if I go towards the left, I'm going towards an infinite grid density. So 0 corresponds to an infinite grid density. And so what you can observe, so in orange and in red, you have the certa and the iterative mobility given here for all of those materials. And in green, you have the certa and the BT Hall factor. And what you can notice is that on an inverse grid size, those quantities are linear and they do converge, but they converge linearly. And this can be shown and it's linked with the implementation in EPW because if you're using the rectangle method, you can see, you can show, you can prove that this has a convergence which is linear in inverse grid density. And so this is also sort of a good news because we could simply, because it's linear, we can extrapolate that to infinite grid density, and then we can have the final value extrapolated to infinite grid density. So something I should mention here, which is a bit technical, is the fact that in all of those equations, you have those Dirac delta. So in the scattering rate, but also in the Boltzmann transport equation. And those Dirac delta can be described by a Gaussian or a Lorentzian. And so in EPW, you can describe them with the d-Gauss input variable with the finite value. And you can also use adaptive broadening. And so this was introduced in this paper. And what it means is that you're going to use a Gaussian with a width which is equal to this formula. And so this means that you will have a different width for each K point and Q points and band. You will have a different Gaussian width. And so this is proportional to the phonon velocity, the electron velocity, also to the reciprocal vector, so basically the crystal, and then it will be inversely proportional to the grid density. So this means that the denser the fine grid, the smaller the broadening will be. And this makes sense because the more points you have, when you do your Gaussian, you want the full width at half maximum to sort of overlap, but not too much because you don't want to lose information. But also you don't want the Gaussian to be too peaked, otherwise the results are very sensitive, and you have no information in between basically. And here I'm showing the result for cubic boron nitride again. This is the electron mobility, and I'm showing the result for the iterative solution and the CERTA for different smearing values. So this is fixed Gaussian smearing, and you can see that I'm basically having those values. I can extrapolate to infinity, and I'm getting the value at infinity. And I'm also showing the value for the adaptative broadening, again extrapolated to infinity. And so now if I show those, so those are the value, but now in terms of the smearing. So I'm starting with the 20 millieV smearing. And this is the value extrapolated at infinite K point and Q point density. And you can see that this is also linear, and this extrapolated to 0 smearing. And what I want to show is that the adaptative broadening solution is close to the one you would get by extrapolating to infinity. So this is a good proxy to get an accurate value without having to do all of the different broadening, because this is quite tedious. You need to converge for different broadening the value to infinity. So it's easier to just do the adaptative broadening and then push that to infinity. Okay, now regarding the Hall factor, those are the results for the 10 materials. And what I want to emphasize is that first, in most material, I mean, in a lot of materials, the Hall factor is not 1. Therefore, it's important to take it into account if you want to compare with experiments. But also, it's temperature dependent. So the Hall factor, for example, increases in those compounds, decreases in those 1, and remain relatively constant in all of those materials. And the value goes from 0.6 to sort of up to 2 in those materials. So now we can sort of ask, okay, how accurate are our prediction or calculation with respect to experimental data? And so here I'm showing the comparison between the calculated mobility versus the experimental mobility. And this is the drift CERTA mobility. As you can see, the comparison with experiment is not too bad. We are a bit typically overestimating a bit, but not too much. This is the mean absolute error in absolute value, and this is in percent, and we overestimate on a bit. Now, if we instead solve the iterative solution, systematically, we will increase the value, and so the mobility will be overestimating experiment a bit. Now, if we also include the Hall factor, then we have this Hall mobility, which is what we should compare, because actually, I haven't said it, but most of the experiment I'm comparing with in this plot are Hall mobility experiments, simply because drift mobility don't exist for those materials. And you can see that in those cases, we quite strongly overestimate the experiment. And so in a way, this is expected because we are only considering electron-phonon scattering. So we are not considering other scattering mechanisms that will reduce the mobility. So we do expect to overestimate experiment. However, it's still quite significant compared to experiments. So we can try to understand why are we overestimating so much by about 100% in some cases. So one reason is the fact that we are computing the electron-phonon matrix elements at the DFT level. And therefore, because of DFT, we are sort of over-screening. So the dielectric function is usually bigger than experiment. And so what I can do, and this is not fully ab initio, what I have done here is to rescreen the electron-phonon matrix element, just rescale them with the experimental dielectric constant. And so those are the black triangle. And so systematically, this will decrease the mobility, bringing it a bit closer to experiment. Finally, what we can also consider is to rescale the effective mass, because also DFT does not always give very accurate effective mass. In this case, it's the agreement is, I mean, it goes a bit in different directions, so this is not very clear. If it will improve, some cases it goes a bit down, so this is not extremely clear. So I think in general, there are some work looking at the effective mass, but I think in general, I think as a community, we need to really look more and focus more on trying to have DFT or another theory to really try to match experiment. Of course, one of the challenges is that experimentally, it's very difficult to get accurate effective mass, I believe, and therefore it's difficult to compare with experiment as well. Okay, just to quickly mention, those three materials, you can see that whatever fully ab initio method I'm using, or even with rescaling, I'm always overestimating quite a lot the calculated mobility with respect to experiment. And so this could be an indication that maybe experimentally it's possible to increase a bit the mobility in those compounds. I should also say that the experiments that I was able to find are quite old, maybe from the 50s, the 60s. And so it's possible that if more recent experiments were done, they might increase the mobility a bit. Now, what you can also wonder is what are the dominant scattering? From which phonons do they come from? And so in very sort of stiff material like diamond, cubic boron nitride, one can compute the spectral decomposition, and one can see that the scattering in those materials is dominated by acoustic scattering, while in more polar materials such as gallium arsenide, then it's mostly optical scattering dominated. I will just then show a few examples of mobility, computed mobility in comparison with experiments. This is in gallium oxide. This is materials used for high power application with a big band gap. And this is the electron mobility compared with experiment in different direction. This is the comparison for gallium nitride. And this was shown yesterday by Feliciano. This is the comparison for MAPI. So this is a perovskite used in solar cell application. This is a very big material with 48 atoms per unit cell. So those are quite challenging calculation. I should mention that actually the mobility here is the CERTA mobility, while the other are the BTE one. Okay, so we can also do metals. And so using this input variable. And so in that case, of course, we don't dope the metal. There is an intrinsic concentration of charge, of carrier in a metal, which is given by the metal. And so what we report is not the mobility, but it's the conductivity, or the inverse of the conductivity is the resistivity. And this is what is reported experimentally. So here you can see the resistivity of lead as a function of increasing temperature. So the resistivity increases. So this was a calculation done by Felix Goudreau in the University of Montreal. And so here we've obtained the conductivity by solving the Boltzmann transport equation or the CERTA, or in the CERTA approximation. And so this will be also discussed in the hands-on later on. And we will also show that there is a more approximated formula called the Zeeman formula, which also gives a relatively good result. But we can also use the Boltzmann transport equation to compute the resistivity of metals. And finally, I want to show this Brook-Ehring model to describe impurity scattering. So this was developed in the 50s, maybe in the 80s, in the age of silicon and semiconductor. And so in particular, those equations have been derived for 3-5 semiconductors. So I don't expect them to work for any materials. And those equations are, rest on parameters that can be computed quite easily by DFT. But this is, of course, a semi-empirical formula. And so once you've computed the ionized impurity limited mobility, you can combine it with the phonon limited mobility that you've computed with the Boltzmann transport equation. And you can use either Mathison rule to combine them and obtain the global mobility. But in the case of those 3-5 semiconductors, there is also maybe a bit more accurate way to connect both. And this is this equation where basically this is the lattice, so electron-phonon limited mobility, and then you have this formula. Okay, and if you do that, then you obtain change of mobility with increasing impurity concentration. So the low impurity concentration, so below 10 to the 15, this is computed, this is phonon limited. So this is computed with the Boltzmann transport equation. And then the reduction of mobility as you increase impurity concentration, this is computed with the model that I showed before. And then you can reproduce quite well experiment and this decrease with impurity scattering. Okay, so I'm done with my lecture. Maybe I was slightly too fast. I took 45 minutes, but then I guess I can answer more questions. These are some books and review that can help you if you're interested in those topics. And that's it. I'm very happy to answer any question you have.
So thank you, Samuel, for a comprehensive talk. So I think you have some questions in Q&A.
Yeah, I see them.
Time is left. Someone can ask also more questions.
Yeah, okay, I can try. I can also take an oral question if some people want. So first, page 16. So page 16, the first formula is without approximation, formally excluding approximation to obtain. So basically the Kadanoff-Baym equation of motion, this is without any approximation, and then we do all of those. So, and you say excluding the approximation to obtain. So this is without approximation. And then in order to obtain the second line, you have to do all of those approximations. So what you do is you block project. When you block project, you take the diagonal. So this is an approximation, diagonal block state projection. Then you can go into frequency, and then you frequency integrate, and then you get this occupation. So you need to do all of those approximations to indeed get the second one. Second question, in the expression for the deformation potential, what is the meaning? Okay. Yeah. What is the meaning of NW? Yeah. This is just the number of Wannier band. Okay. So as you can see, here we are summing over bands. So this is an object that is band independent. So we can sum over all the bands, but because we're using Wannier function, we Wannierize a number of bands. And so I'm summing over all the band NM, and this is just the number of bands that I'm summing on. So the deformation potential is renormalized by the number of bands I've summed on. Then Jaimo Lim, could you elaborate on what you mean by velocity, where you explain the convergence with respect to the coarse grade? Yeah, so I don't have a direct slide for that, but yeah, maybe so this yeah, I could explain more maybe during the hands-on, but basically the electron velocity, where is it? Let me show you. Right. Okay, let's say, yeah, the electron velocity here, there are two ways to compute it. You can use a Wannier approach to express it. And this is what was used in the result that I have shown. But you can also use sort of a dipole approach where you have the P over M, so the momentum, and then you have to take the commutator between the non-local potential and the local one. And so far, for a very long time, what was implemented for historical reason in EPW, we were neglecting for simplicity this non-local part, and this is what we call the local velocity approximation. And this was not giving very good results, but very recently, Yun-Jun added basically this commutator, and therefore this is a second way to compute the velocity, which does not depend, directly on the Wannier function, and that converges a bit faster. However, this is not shown in the result because this is very recent. But yeah, so those are basically the two ways to compute the velocity.
Sorry, Samuel, there is also a hand raised. So
yep.
maybe
sure. I can
go on.
Could you hear me?
Yep, perfect.
Okay. So no, I wanted to ask that would long-range Friedel oscillations affect the transport properties like this carrier mobility, and can
sure. You said Landau, correct? Yeah, Landau level. Yeah, sure. So
no, the Friedel oscillations, long-range Friedel oscillations because of the impurity scattering.
Yeah, so the whole theory is without impurity scattering. At the end, I was just showing a model, but there is no impurity scattering. With respect to the magnetic field, I should also mention that if you put a very large magnetic field, you will start to get Landau level. And of course, this whole theory breaks down. So this is only valid in the limit of small magnetic field. So if you're in that limit with no impurity, then yeah, those are the equation, and you don't have such oscillation. Yeah.
So to study impurity scattering, I cannot use this EPW code, right? like to study?
It's not fully ab initio, and to my knowledge,
okay.
I think maybe some Green's function, direct Green's function method might compute that, but I'm not an expert. I don't know. Yeah.
Okay, thank you.
Sure, you're welcome. Does the adaptative
question, like from Jun's work?
Live, or you want to continue?
Live.
Yeah, okay.
Junso, you need to turn your microphone on.
Oh, hi.
Hello.
Yeah, I was wondering if you have tested the behavior of the polar optical scattering, polar optical limited mobility with respect to screening. Screening that is dependent on doping and carrier concentrations.
Yeah, so I mean, in a way, the polar optical is included because we include all modes. So it's not something we have to add, let's say, per se. And if you, so in this case, I haven't studied, so all the doping is always in the regime of this intrinsic doping where the mobility does not change as a function of doping because we are in this low carrier concentration limit. And basically the Fermi level will always be in the conduction band. So in the hands-on that you will do, basically the Fermi level will be determined such that you have a given carrier concentration. Now, of course, it's true that if you start doing very heavy doping, then the Fermi level will be inside the conduction band. And of course, this will have an impact because you will have more screening. And of course, the matrix element will be more screened. You might lose things like LOTO splitting and things like that. So I haven't investigated this, but yes, of course, this will have an impact, yes.
Thank you.
Does that answer the question?
Yeah, more or less. I was wondering if you have plans to test it in the future.
Yeah, not really.
Not immediately. Okay, thanks.
Yeah. So
Samuel,
I can add. I mean, myself, no, but I mean, there are people in the group of Feciano, like Carla Verdi, who did that. And then what you have to do is you have to add some screening. And in EPW, there is also this capability through some models. So you can, for example, use what's called the Thomas Fermi screening or RPA screening to take those effects into account. And so this is possible in EPW through those screening models. So you can screen the electron-Phonon matrix element to take that into account. Yeah.
Right, okay, thank you.
Samuel, I think we have time for another live question.
Yeah, sure.
So it's Walter. So Walter, go on.
Hi, so very nice talk. I have a little bit more of pedagogic question in a way. In most textbooks, these Boltzmann transport equations are kind of derived based on the semi-classical approximation where you're talking about how wave packets are moving. And you derive the whole thing from Green function, which I found quite interesting. But what I'm wondering about is what is the new physics that's included by doing it that way? I mean, of course, in the Boltzmann equation and the scattering times are just empirical parameters. And that's, of course, calculated by the whole perturbation theory. But what's the advantage of deriving the Boltzmann formalism itself from the Green function versus semi-classical equations?
So that's a great question. And indeed, so in many textbooks, indeed, it's called, I believe it's called semi-empirical because the idea is that the carrier propagate classically and then they interact quantum mechanically. This is my understanding. So this is why I call it semi-classical. And what we try to show here is that you don't need to be semi-classical. And so, in fact, I believe the Boltzmann transport equation is not semi-classical. It's basically a quantum mechanically derived formula that you can obtain with well-defined approximation. So I don't think we should call it semi-classical, in my opinion. And so the new physics, I mean, in the end, you could obtain from semi-empirical argument, you could obtain something similar indeed to this equation here. So I don't think in that regard you have new physics, but the advantage of doing this derivation is that now we have very well-defined approximation. And therefore, we can try to look at which one we could remove to try to move towards a more, a more accurate equation, which I think was not possible from, an empirical derivation or semi-empirical derivation.
I see, but we're still discussing the whole time basically diffusive transport and not ballistic transport regime, right?
Oh yeah, yeah. So yeah, this is totally true. So the Boltzmann transport equation, of course, is not valid at very, very low temperature. So indeed, if you do the calculation, this will explode and go to infinity, which of course we know it's not the case. And if you go to very low temperature, you need to start having this ballistic regime. And then, so I haven't done the connection, but I'm pretty sure that indeed, those Green's function, non-equilibrium Green's function method, maybe in siesta and codes like that, which do ballistic transport, one should be able to connect basically those methods directly and show, where the approximation are to be able to connect them. And maybe there might be a way to have a full theory or to have an extension of the Boltzmann transport theory, which would also describe the low temperature regime, ballistic regime well. This, I think, would be a very exciting global formula, I think, yes. That would be really interesting.
So I think, Samuel, we have time for a short question maybe from Mao Yang.
Thank you for your talk. I have a question about the result of ProSkies on page 32. To calculate the relaxation time of ProSkies, is the by-water term included, and does the by-water term contribute more than Fan term in ProSkies? Because yesterday you showed that the temperature dependent gap of ProSkies and the high order term contributes more and can so the band gap can increase with temperature. Thank you.
Yeah. So basically the whole theory of carrier mobility is closely linked with the imaginary part of the electron-Phonon self-energy. And the Debye-Waller term is a real term. Therefore, it does not enter in the calculation of the mobility. So you have no Debye-Waller term. So it's not included in the mobility. Now, you are correct that if you want to compute the change of band gap or the change of bands, in that case, it's proportional to the real part of the self-energy and the imaginary part. And this was not included. So when we did those mobility calculation, we consider, basically the GW band gap, GW band factor. And so we did not include the change of temperature. So if you move the temperature here, the band structure is the same all the way through. However, you need to also consider the fact that the band gap has almost no effect on the mobility itself, right? The only thing that has an impact is the effective mass, so the change of band curvature. So if the band gap is very wrong, it doesn't matter at all. The only impact it will have on the mobility is if the band curvature, basically the electron velocity, if that changed, then it will have an impact. So it's not very crucial, I think, to describe the change, except if the band curvature changed a lot due to those renormalization effects, but I don't think it's the case. For silicon, for example, it's maybe 1, 2, it's very small. Yeah.
Thank you.
So thank you, Samuel, once again. I think, there are some questions for you like to type in Q&A.
Yeah.
So let's continue now with